Okay, thank you. Yes, as it was saying, my name is Sofia, and I'm a researcher in cryptographic things, but also an implementer of cryptographic protocols. So today I was wanted to have a talk in which I talk about which kind of tools we have found useful in order to implement a cryptographic protocol as OTR version 4. Oh, it doesn't work. Okay. Okay, now it works. Okay, so basically to give a little bit of a context, what is OTR and what is a cryptographic protocol? So basically, what is defined as a cryptographic protocol? In order to answer this question, we first have to answer the question, what is a protocol? A protocol can be defined as a set of rules. We try to attain certain definitions. We try to give the end user certain definitions. In the case of a cryptographic protocol, this basically means that it's a protocol which uses cryptographic algorithms in order to attain certain security and cryptographic properties. In the case of OTR, for example, the security properties that this protocol tries to attain are the properties of deniability, security, and some privacy properties. But what is OTR? OTR stands for off-the-record messaging protocol, and it comes from the idea of journalism of the record, which basically means that if a journalist is having a conversation with a source, this source, when the article gets published in a newspaper, on the television or radio, the source remain anonymous. There's no way to link whatever is said in the article with the identity of the source. Something that three cryptographic researchers by the name of Ian Goldberg, Nikita Borisov, and Eric Brewer realized in a paper in 2004 is that this actually is not attained in the digital conversations that we have in the digital world. Why? Because when we have conversations in the digital world, we always leave a trace of our identity in whatever conversation we take place. So what they argue is that digital conversation should mimic real, casual, physical conversations in the sense that, for example, if I have a conversation with someone, let's say Bob, and I say, hey Bob, I really hate my job, and then Bob goes to my boss and says, Sophie said this, then I can always deny having said so, or even haven't participated into a conversation with Bob. That's a property that I have in the real world, but it's not a property that I have in the digital world, because in the digital world, Bob can go and show to my boss that I had a chat over whatever chat client, and that this is what I said, and that I indeed had a conversation with someone. So basically what the cryptographers wanted to attain with OTI is basically give a mathematical way in which it cannot be proven that you participated into a conversation or that you said a specific message into a conversation. What they also argue in the paper is that they compare the OTR protocol with another cryptographic protocol by the name of PGP, which stands for Pretty Good Privacy. Pretty Good Privacy is a way in which you can encrypt conversations in a secure way, but one of the problems with PGP is basically that you will use the same key to encrypt the messages. So what the three cryptographers argue in the paper is that this is a property that is not actually something wanted, because this means that if an attacker can get hold of this key, they can actually decrypt past messages or future messages with this key. Okay, so that is basically OTR. So basically the security properties that we want to attain is basically the security in encryption. We want to attain deniability in all of its forms. And yeah, so the communication remains not linked to the identity of the participants. Why we decided to do a version 4 of OTR, there has been already previous versions, but one of the reasons why we decided to update as a team this version is because we wanted better deniability properties. Something that happens quite a lot in the cryptographic community is that the academia comes with more specified definitions of security properties. So it's not enough to just create one protocol in the past and then expect that this protocol is just perfect and it will work for any future years. It's actually mandated that the cryptographic algorithms and the cryptographic definitions gets updated as the academia also updates the definitions and the algorithm. So we wanted to provide better security properties in regards to deniability and in regards to the security algorithms. We wanted to provide this forward secrecy and post-compromise secrecy, which is what I told a little bit earlier. That is that if an attacker gets hold of a key, this attacker cannot retroactively decrypt past or future messages. And of course, we wanted also to update the cryptographic algorithms. We wanted to make the protocol more efficient, more fast, and yeah, all that jazz. Okay, but with the design of the protocol, everything was nice, and we had our mathematical definition, the cryptographic proofs, the designing in general of the specification. With implementations, there was some constraint and some limitations that we found, especially because with the modern cryptographic protocols, you will find that modern cryptographic protocols handle at certain points 9 keys or a lot of passphrases or a lot of passwords, and this actually is sometimes challenging when you're using programming languages that have some memory management issues, because you will have to take into account when this secret-sensitive material is created and when this secret-sensitive material has to be securely wiped or released. Okay, so for the implementation of the protocol in its version 4, we decided to implement it in C. Why we decided to implement it in C? Because C is still one of the most portable languages there are, because it's sometimes also a standard to create a library in C, so other programming languages later can take inspiration of this main library and implement themselves. The library is called EuroLLVM if someone wants to look it up. But of course, with the usage of the programming language C, it comes some memory management issues. Of course, as we all know here, I think, buffer overflow, memory leaks, some issues of free, for example, use after free, double free, invalid free, usage of uninitialized memory or garbage data, overlap of the source and destination pointers and memory copy. And I can tell you right now that we had all of these problems during the implementation in C at a certain point. Okay, so why this is an issue for a cryptographic implementation of a protocol? Okay, I put a quote from this paper that's actually an introduction to Bulgarin, which is a nice tool, but it's not enough. But I basically put this quote because there's some part that is very important in the sense that it says, memory leaks are hard to find because a program might work just fine for a while and then crash without apparent reason, simply slow down below acceptable levels. And why I think that this part of this quote is important is because it's really important when using a cryptographic protocol and doing an implementation of a cryptographic protocol, because it's really not enough to just expect that a program crashes in order to know that some sensitive or private information is being leaked, or just expect that a user will suddenly realize that their sensitive information is getting leaked because their program slowed down. It's actually mandated that implementers take into account the sensitive private information that they should take into account while developing an implementation. Of course, in cryptographic protocols, more than any other implementation of anything else, you will always have some private secret material, especially encryption keys, private keys, passwords, passphrases, message keys, and a lot of other material that should not that an attacker should not get hold of. Of course, from a mathematical perspective, if, for example, if an attacker can get hold of a key, you always define what an attacker can do when they get hold of a key. There's a very nice property lately on the messaging protocols that is called the post-healing nature of some cryptographic algorithms, in the sense that even if an attacker gets hold of a key, then the algorithm will heal itself and the keys will get renewed, so it doesn't really matter that much if an attacker gets hold of a key, but it still is something that we shouldn't strive for. And of course, it's really important to actually always think about the memory management issues of a programming language, because as a talk recently from the Microsoft Research Group presented, the memory issues remained dominant as a way of attackers actually getting hold of private information, especially in the sense of heap out of bounds, either read or either write. So something that when we started the implementation of the project, we decided to give developers some kind of tips in order to safely handle memory-related issues. But as we will talk in a moment, that was not enough. So most of the problems came of developers actually not thinking about the scope of variables. So oftentimes when they malloc anything, a variable, a structure, a pointer to a structure, or whatever, they forgot to free. And this happened very, very often. This, after a little research that we did, doesn't even happen when you create a new library, but actually most of the cryptographic libraries that you will find out there have, at some level, a lot of memory leaks. We also tried to give them the idea that not work with the original pointer, but rather with a copy of it. This actually didn't help that much because people, again, forgot the scope of the different pointers. Something that happened quite a lot is that developers used to free a pointer to a struct, but not the internal fields inside of a struct. So if it is a struct that was malloc, but inside of it there was another pointer, developers oftentimes forget to free the inside pointer. And of course, one of the things that we tried to implement at first in the project was the usage of Valgrind. But this has a lot of limitations. It's a great tool, but it has some limitations in the sense that sometimes it crashes, in the sense that there's a lot of false positives, especially in the newer versions of macOS. And it has a lot of installation problems, also again in the newer versions of macOS, especially in High Sierra. So it was not that easy to actually only use the Valgrind memory checker tool. Something that I like about the previous talk was actually that there was some thinking about side channels attack and hardware attacks that you can have. Cryptographers often argue that any computations and only computation will leak at certain point information. There has been some proposals from some cryptographic protocols on how to actually create cryptographic protocols that per se in a mathematical way are resistant towards side channels attacks, for example, but they have never been really developed in a production level. So we always come with the assumption that at some point information will get leaked. But that doesn't mean that we shouldn't take like all of the considerations to actually take into account memory management issues. Of course, in cryptography, you will always have the antagonism between public information getting leaked and secret information getting leaked. At a certain point, we shouldn't strive for any kind of information to getting leaked because public information, in a way, can be correlated sometimes with secret information or from sensitive information from a user. So it shouldn't be possible to actually, we shouldn't strive to actually leak anything. An example, of course, if you want to know about a very interesting memory management issue-related attack to a cryptographic protocol, there's a Heartbleed attack that was done to TLS that is very interesting. Okay, and there's a lot of problems that you will find in cryptographic protocols while doing the implementation of the version 4. We also find another problems with other libraries that were either a dependency or some libraries we will take in inspiration from. There's little to no testing. The code sometimes does not run or compile in many operating systems. Sometimes it doesn't work in many compilers. The code is difficult to understand, the code is not clean, and of course there's no usage of tools for checking memory issues or related issues. And we have found, I will say that at least 70% of the libraries that we researched had at least some kind of memory management issues when we run them with Valgrind or when we run them with other sanitizers, for example. Okay, so in OTR what we try to strive is actually test it in different machines and in different compilers, GCC and Clang especially. And we decided to test it in different tools and try to see what outcome the usage of different tools gave us. So we tried to test it with Valgrind using Mencheck, Helgrin, DRD for threat safety, but we also tried to use the Clang tools as address sanitizers, Clang tidy, Clang format. And at certain points, we also decided to implement new ideas that some cryptographic community has had, like, for example, building constant time checkers on the top of Valgrind to check the constant time of cryptographic algorithms. For the future, we have also been thinking of doing fuzzing or tainted analysis. And of course, we also passed the project with a lot of compiler flags. This is something that most of the libraries related to security don't do. I'm unsure why, but yeah. Okay, so what kind of useful tools we have found? One of the first useful tools we have found to actually test correctly the implementation is the usage of address sanitizers. In comparison to Valgrind, this was actually much more useful to use. Why? Because some of the people who were part of the implementation team of OTR before didn't have a lot of experience of actually working in C or implementing in C, and the output from Valgrind was sometimes not very user-friendly in the sense that sometimes it flagged false positives, sometimes the output was unreadable, sometimes it flagged the same issue on several parts of the code, so it was really difficult to understand. And something that we find by using address sanitizers was that it was really clear the error messages of what was happening in certain memory leak or certain problem with heap out of bounds or certain problems that you can find. It's also very useful to find bugs locally in most operative systems. As I said, Valgrind doesn't quite work that well on macOS, so actually using something like address sanitizer was actually super useful. The limitations, of course, is that when you're creating a cryptographic library, you create this cryptographic library to be called by certain other clients. For example, in OTR before, we created a cryptographic library, and then other client messaging applications were the one that actually called this library, which means that this library is not executed itself, but rather, for example, executed when we test. So one of the things that we found out is that, of course, address sanitizers would only work on the positive tests that we had or in the paths of the tests that we use. So for example, paths that were not tested were not covered by the address sanitizer. So of course, for this, we used another tool, a static analyzer. We tried to use at the beginning, we successfully used at the beginning Splint as a static analyzer, but something that we found out as well as in the comparison between the address sanitizers and Valgrind was that Splint was very difficult for developers to actually understand and know what was going on. In the sense that, for example, Splint requires a lot of annotations, annotating a function if it's null or not null to actually work. It has a lot of passing issues in regards, for example, that variables should be declared at the start of the function, and there's a lot of issues to actually make it work. It is a great tool, but we find that it doesn't have a lot of user experience friendliness. With Clang Tidy, it was really easy to actually implement and put it into the code. We use it for its static analyzer tool, but also because it has some, I will call it styling recommendations in the sense that it can also flag things like functions that are not used when there's unused variables, etc. So it was really, really useful for people to actually use this, also in the sense that Clang Tidy actually showed exactly in which line, for example, a potential memory leak was happening, so it was very nice. It also helps a lot of people to onboard on C because it gives you a very nice stack trace of what is going on when a potential memory leak happens, for example. And of course, the last thing that we use in the project is in regards to style. Something that happens is that a lot on cryptography is that people create a cryptographic library in whatever language, and they don't put it any documentation, or the style is really not that nice. So when people try to use this cryptographic library on a client application, for example, they found it really hard to actually use this cryptographic library. And we thought that we have the responsibility of giving other developers that are not security experts or cryptographic researchers to actually have a good way to call a library, a cryptographic library, inside of a client application. This is something that actually doesn't happen that much around cryptographic libraries, and there's this thought that cryptography is very difficult. Cryptography is actually very complex, yes, but it can be easy if people put enough documentation or if the code is clean enough to be used. So of course, we found a lot of unused variables or functions. We found a lot of exposed functions that were not actually defined anywhere in the code. We found a lot of ignored return values, and we tried to tackle all of them. Something that we also try to tackle is that the project should have a style that is consistent from every developer on the team, in the sense that sometimes people coded with some indentation and some other coded with another type of indentation, so we try to enforce that. And something very funny that we did is that we put also the styling direction on the CI, so when someone forgot to do a style, they would get flagged on the CI. Okay, so awful issues that we find while doing the implementation of the cryptographic protocol. As I said, at a certain point, for example, in OTR, you will have to handle like 9 keys in memory, and you will have to know exactly what kind of a scope those keys has. And this is something that is many cryptographic protocols have been pushing around. The Signal protocol also handles at least 7 keys at a certain point. There's an upcoming MLS protocol that will also handle a lot of keys at a certain point. So it's really useful to have some kind of tools that will help you to know what a scope a key has and if this key is actually not released. So the awful issue that we first found out, and it took a lot of time to actually solve, is that at a certain point, Diffie-Hellman keys were released and later tried to be reused. This happened because on the protocol, we defined that keys sometimes are derived depending on how many times the protocol has run. So for example, Diffie-Hellman keys only get generated every 3rd time that a certain part of the protocol gets run. So at a certain point, some developers try to free this key at the second time that the system ran, and then other parts of the system try to access it. And it was very difficult to actually try to find out when was this happening, because in a complex cryptographic protocol, it's really difficult to know at what certain point things are getting leaked or not. We had a lot of the usual memory management issues, a lot of double frees, a lot of uninitialized values everywhere in the protocol. And of course, people constantly forget to free. Okay, so why are these kind of tools like address sanitizers and client ID needed? They are needed because sometimes implementation of cryptographic protocols can be complex enough, not difficult, but complex enough in their implementations. Developers have to handle a lot of cryptographic algorithm, understanding of cryptography, understanding of security issues, plus they also have to deal from some memory management issues. So actually giving programmers and developers a tools to check whatever they are doing is actually a very nice idea. In the sense that programmers are not perfect, the code that they will release will not always be perfect, and that's okay. But at least having some tools to check whatever is getting pushed is a nice idea. And of course, while these tools also are needed, is because, as I said, Valgrind is a great tool, Splint is a great tool, but sometimes these tools don't catch up with some development operative systems, so it's good to always have at least other tools that you can use in replace of. Okay, and the final idea that we have, something that we found out is that it will be, okay. Really? Okay. Something that we found out is that, something that we found out is that really it will be really nice if there's some way actually to put in a certain level what the scope of the secret private information is. Because what happens is that, for example, in the code, what we try to do is that we try to create an annotation that said, okay, this is secret information, and this is the scope of this secret information, so please release it after this scope is met. But it will be really nice if there's some kind of warning, and we have been thinking about doing something like this, some kind of warning that actually said, okay, this is a sensitive variable, this is a private sensitive information, please use it until this is scope. Because something that we have found out is that, of course, public material can get leaked, but it's more okay if public material get leaked, but in a cryptographic protocol it's much more important to take into account this private sensitive material. And yeah, that's all. So, some references you want to think about it. Thanks.
Sorry for the mistake. Thank you, Sofia. Do you have questions?
Oh, nice.
We are ahead of time, so. So I have one question. As far as I understand, okay, there is the implementation of the protocol, and then the protocol relies on some cryptographic primitives. As far as I know, there are implementations that are proven secure, such as SALT, or there are other ones. Did you look at that libraries and if there would be interesting to use in your project?
Yeah, I will say. There's some implementations of security protocols that have been found secure to a certain level because, for example, they have submitted the code base to certain security audit firm to check if the security of the protocol was actually correct, etc. But most of the times when cryptographic protocols start to get implemented, they don't take into account the security issues. It's only after, for example, someone finds an attack or developers realize that maybe they should be taking into account the security issues that they start using these tools. And what I will argue is that actually most of the tools should be there since day one, because it's much more easier to fix things since day one than try to fix it in the past, something that was done in the past. The libraries that I have analyzed, most of them will leak information at a certain point, and you will find everywhere in every repository that most cryptographic libraries will have issues raised around memory management issues.
Did you consider just re-implementing your application in Rust? Because if memory leaks is such a huge burden for you, it seems like the perfect match. So did you try to see to
Yes.
Okay.
So this is a question that gets often asked nowadays in regards to cryptographic protocols. There's some cryptographic protocols that are actually getting rewritten. Also, parts of it are getting rewritten in the Rust programming language. C still remains as a programming language that is most portable in most systems, so that's why you usually have a library that's written in C. That said, probably our cryptographic implementation, we are doing some effort to do it in Golang as well. There's some people doing in Java and Python, and probably there will be a Rust Lang as well.
OK, so thank you, Sofia, again.
Okay.
Tu veux qu'on attende ou